Hello, and welcome to Space for Sleep. In October of 2017, a point of light crossed a sequence of digital images taken above the island of Maui. It did not look like a visitor from another star. It did not look like anything at all. There was no resolved surface, no visible outline, no photograph showing a long red object turning against a field of stars. The famous images that later appeared in newspapers and documentaries were paintings. The real evidence was quieter, a few pixels, changing position from one exposure to the next. From those moving pixels, astronomers learned that the object was already leaving. It had passed close to the Sun weeks earlier, unseen. It had crossed the orbit of Mercury, curved through the inner solar system, past Earth at a safe distance, and begun fading into the darkness beyond the planets. By the time anyone understood what it was, the best part of the encounter was over. The object was named Oumuamua. The name is Hawaiian. It is commonly translated as a messenger from afar arriving first, with a sense of something reaching out ahead of others. The spelling begins with the character called an okina, marking a break in the sound. The name was chosen in the place where the discovery had been made, and it carried an implication that later proved unusually accurate. Oumuamua was not merely a distant object. It was the first confirmed macroscopic body ever observed entering the solar system from interstellar space. For generations, astronomers had expected such objects to exist. Planetary systems are not gentle places during their youth. Planets grow by collisions. Giant planets scatter smaller bodies. Binary stars exchange energy with passing debris. Comets can be thrown outward so strongly that they escape the gravity of their parent stars and begin wandering through the galaxy. The Milky Way should contain immense numbers of these discarded fragments. Yet none had been recognized until a survey telescope called Pan-STARRS found one in 2017. Robert Warwick, working with images from Pan-STARRS 1 on Haleakala, noticed the moving source on October 19th. The survey was designed to find objects that change position or brightness, including asteroids that might approach Earth. Warwick compared images from different nights and found the object in earlier data as well. The additional positions allowed its orbit to be estimated more accurately. At first, it received an ordinary temporary designation. Then the orbit refused to become ordinary. Most objects moving around the Sun follow ellipses. Their paths may be nearly circular, like Earth's, or extremely stretched, like the paths of long-period comets. But if they remain gravitationally bound, the orbit closes in principle. The object can travel far away and take centuries or millions of years to return, yet its total orbital energy remains below the escape threshold. A parabolic orbit sits at the boundary. A hyperbolic orbit lies beyond it. For a body on a clearly hyperbolic path, the Sun's gravity bends the trajectory but cannot capture the object permanently. It arrives with speed left over even when imagined infinitely far from the Sun, accelerates as it falls inward, turns around the Sun, and departs with speed left over again. Oumuamua's measured eccentricity was not just barely above the boundary because of a small error or a close encounter with a planet. Its incoming path was unbound before it reached the region where the planets could have scattered it. The excess speed at great distance was about 26 kilometers per second. The conclusion was unavoidable. The object had approached from outside the solar system. This was established by motion, not by appearance. No sample was collected. No chemical signature identified a particular alien star. No camera saw a landscape that could not have formed here. The proof was written in the geometry and speed of the orbit. That distinction matters, because almost everything else about Oumuamua is less certain than its origin. Its interstellar trajectory is secure. Its exact shape is not. Its exact size is not. Its composition is not. Its place of birth is not. And the physical cause of its small additional acceleration remains debated. The story, therefore, begins with an unusual mixture of certainty and ignorance. Astronomers knew where the object had not come from before they knew what kind of object it was. Its path through the inner solar system can be reconstructed backward. Oumuamua crossed perihelion, its closest point to the Sun, on September 9, 2017. It passed at about 1/4 of the distance between Earth and the Sun, while inside Mercury's average orbit. At that time, it was moving at nearly 88 kilometers per second relative to the Sun. Its speed increased by the long fall into the solar gravitational field. No telescope recognized it then. Its closest passage to Earth occurred in October, several days before discovery. Even that approach was not especially close in the scale of near-Earth objects. It remained tens of millions of kilometers away. There was never a danger of collision. The delay was caused partly by geometry. Near perihelion, Oumuamua appeared close to the direction of the Sun in Earth's sky, where ordinary nighttime surveys could not search effectively. Only after it moved into a darker part of the sky and came close enough to Earth to brighten did Pan stars detect it. The late discovery imposed a permanent limitation on everything that followed. Astronomers had not watched the object heat on the way inward. They had not measured its behavior near the Sun. They did not know whether it had once possessed a bright coma that faded before discovery. They did not know its brightness before intense solar heating changed the surface. They had only the outbound portion of a brief encounter. Once the interstellar nature became clear, observatories around the world turned toward it. Large optical telescopes measured its brightness and color. Hubble extended the astrometric record after ground-based observations became difficult. Infrared observations searched for thermal radiation and gases. Radio telescopes looked for natural emission, and because the object had become publicly associated with speculation about technology, several groups also searched for narrowband artificial signals. Every observation competed with fading. A small body reflects less sunlight as its distance grows. The sunlight reaching it weakens with the square of its distance from the Sun, and the reflected light spreading toward Earth weakens again with distance. The combined decline can be severe. A target that is merely difficult 1 week can become unreachable soon afterward. The observation campaign did not last only a few nights, but the useful window was still short. Optical astrometry continued for several months with increasingly powerful instruments. By early 2018, Oumuamua had become too faint even for Hubble. What remained was a record of positions, brightness measurements, colors, and upper limits. An upper limit is a quiet kind of evidence. If a telescope looks for carbon monoxide and finds none, it does not prove that no carbon monoxide exists. It means the amount must have been below the sensitivity of that observation under the assumptions used to interpret it. If an image shows no dust coma, it does not prove that no molecules left the surface. It means there was no dust cloud bright enough and extended enough to be detected. If a radio search finds no narrow signal, it does not prove that the object is natural. It rules out only transmitters operating within the frequencies, powers, beam directions, and times that were observed. Much of the Oumuamua debate grew from the difference between absence and non-detection. The object was unresolved in every image. This is another important correction to the familiar picture. No telescope photographed a cigar. No telescope photographed a pancake. The source remained smaller than the angular resolution of the observations, appearing as a point against the sky. Shape had to be inferred from the way the point brightened and dimmed. As Oumuamua rotated, its reflected light changed dramatically. At some times it was more than 10 times brighter than at others. A body with a uniform surface can produce a large brightness range if its projected area changes greatly during rotation. A long object seen broadside reflects much more light than the same object seen end-on. A flat object seen face-on reflects much more than it does edge-on. This led to the famous claim that Oumuamua was extraordinarily elongated. The earliest simple interpretations treated the body as a rotating ellipsoid with roughly uniform reflectivity. Under those assumptions, the brightness variation required a ratio of longest to shortest dimension of at least about 5:1 and possibly much larger. Artist impressions turned that estimate into a dark, narrow spindle. But a light curve does not provide a unique three-dimensional shape. It mixes shape, surface reflectivity, viewing angle, illumination angle, and rotation state. A body with bright and dark patches can vary without being as elongated as a uniformly colored body. A flat disk and a long rod can create similar changes when viewed under different orientations. Sparse observations leave room for multiple models. Later physical modeling found that both an elongated, cigar-like form and a flattened, disc-like form could reproduce important features of the light curve. In one influential analysis, the preferred oblate solution was roughly 6 times wider than thick, while a prolate solution was roughly 8 times longer than wide. The disc-like model was statistically easier to view at an orientation that produced the observed deep minima, but the result did not transform the object into a known pancake. It identified one family of models as more probable under particular assumptions. The safest description is therefore less visual. Oumuamua had an extreme brightness range and an unusual shape or surface pattern. It was probably far from spherical. The available light does not tell us exactly what outline it possessed. Its rotation was also more complicated than a single clean spin. Different groups found apparent periods near 7 or 8 hours, but no one simple period repeated the brightness pattern perfectly. The object was tumbling in a non-principal axis state. Instead of rotating steadily around the axis with the greatest stability, it combined motions, causing its orientation to change in a more complicated rhythm. A thrown book can tumble this way. An asteroid can enter such a state after a collision, a tidal encounter, or a torque created by uneven loss of gas. In small bodies, internal friction slowly damps the motion, but the damping time can be extremely long. Estimates for Oumuamua allow the tumbling to persist for at least hundreds of millions of years and perhaps much longer. The tumble was evidence of a history, but not a readable biography. It did not tell astronomers whether the disturbance occurred in the parent planetary system, during ejection, during travel between stars, or near the sun. It did not prove that jets were active during the observations. It only showed that the body was not rotating in the simplest possible way. Its color was moderately red. This did not make it exotic. Many asteroids, dormant comets, Jupiter Trojans, centaurs, and Kuiper belt objects possess reddish surfaces. Irradiation can transform carbon-bearing molecules in ice and dust into darker, redder residues. Long exposure to cosmic rays in interstellar space might contribute to such processing, but the color alone could not measure the duration of the journey. Some observations suggested modest color variations as the object rotated. Those differences were uncertain and could have come from noise or from real patches on the surface. Again, the evidence offered possibilities rather than a portrait. Size was tied to another unknown, albedo. A small bright object and a large dark object can reflect the same amount of sunlight. Without resolving the body or detecting its thermal emission, astronomers could not directly separate size from reflectivity. The Spitzer Space Telescope searched for infrared radiation from Oumuamua and did not detect it. That non-detection limited combinations of diameter, albedo, and surface properties. If the surface was dark, the object had to remain below a certain size. If it was bright, it could be smaller. Depending on shape and albedo assumptions, characteristic dimensions range from tens to a few hundreds of meters. This uncertainty is large in percentage terms and small in astronomical terms. Oumuamua was not a planet. not a moon, and not a vast spacecraft kilometers long. It was a minor body, comparable in scale to a building, a city block, or a small hill. Its mass was even less certain because density was unknown. A compact rocky fragment, a porous icy body, and a fragile aggregate can share the same brightness while differing greatly in mass. Yet mass became central to the mystery because the same force produces more acceleration in a lighter object than in a heavier one. Before the acceleration was announced, Oumuamua was already unusual. It was interstellar. It tumbled. It had a large brightness range. It showed no visible coma. None of those properties required a new law of physics. Then astronomers compared its measured positions with the path predicted by gravity. The small difference between them changed the entire discussion. The motion of a small body through the solar system can be predicted with remarkable precision. The sun provides most of the acceleration. The planets add smaller pulls. The moon, large asteroids, and the changing positions of these bodies can be included. The observations themselves carry uncertainties, and observatories have tiny systematic differences, but a long arc of accurate positions allows competing orbital models to be tested. For Oumuamua, a model containing gravity alone did not fit all the astrometry. The discrepancy was small, near 1 astronomical unit. The additional acceleration was only a few millionths of a meter per second squared, roughly 1,000th of the sun's gravitational acceleration there. A person could never feel such a push. Over weeks and months, however, it shifted the predicted position enough to be measured. The 2018 analysis that established the effect used observations from ground-based facilities and Hubble. The detection was statistically strong. Adding an outward acceleration directed approximately away from the sun produced a much better description of the trajectory. The best-fitting simple forms decreased with heliocentric distance. An inverse square law worked well. An inverse distance law could also describe the data. A later independent reanalysis confirmed that a radial, outward non-gravitational term was strongly preferred, while showing that the exact distance exponent was not uniquely pinned to 2. This nuance matters. The common statement that Oumuamua's acceleration followed sunlight exactly is too strong. Solar radiation intensity falls as the inverse square of distance. The measured motion was compatible with that pattern, but the observing arc and uncertainties allowed a range of distance dependencies. The direction and magnitude were real. The detailed law was less exact than a neat summary can suggest. The term non-gravitational acceleration does not mean anti-gravity. It means only that gravity by itself was insufficient. Comets experience such accelerations routinely. Sunlight warms their surfaces. Ice changes directly into gas. Gas escaping through pores or vents carries momentum. The nucleus recoils in the opposite direction, like a weak and uneven rocket. This was the explanation favored by the team that measured Oumuamua's acceleration. The object could be cometary even though it looked inactive. That answer is physically conservative, but it immediately creates questions. Where was the coma? Where was the dust? Where were the gases that should have produced the thrust? Deep images showed no extended cloud. Spectroscopy placed upper limits on common molecules. Spitzer found no infrared source and constrained carbon monoxide, carbon dioxide, and dust production. Other observations did not reveal the hydroxyl emission commonly used as a sign of water. A standard active comet at the inferred level of thrust might have been expected to announce itself. Yet standard comets are not a single uniform category. Some release gas with little dust. Some possess surfaces that suppress visible activity. Some lose molecules that are difficult to observe at particular wavelengths. Some are so small that a modest mass loss rate produces noticeable acceleration without forming a spectacular coma. The real question was not whether outgassing could move a body. It was whether an outgassing model could satisfy all the constraints at once. The answer depends on composition, size, shape, albedo, thermal conductivity, active area, gas speed, and the geometry of the jets. Most of those quantities were not measured directly. Water ice is the most familiar cometary volatile. Near the Sun, water sublimation can provide substantial recoil, but enough water outgassing to produce the acceleration might also have released detectable products or dust. Models that use ordinary water therefore need a surface and internal structure capable of hiding the usual signs. Carbon dioxide and carbon monoxide are more volatile. Spitzer's non-detection placed meaningful limits on both. Those limits did not forbid every possible distribution of gas, but they made simple versions less attractive. The object's rotation added another issue. An off-center jet should create torque as well as linear acceleration. A small, elongated body can be spun up strongly by persistent asymmetric outgassing. Some calculations argued that the required thrust would have changed the rotation rapidly or torn the body apart. Yet the observed light curve did not show a simple dramatic spin-up. Other models found that a jet following the subsolar region of a tumbling body could provide thrust while producing torques compatible with the complex light curve. The disagreement was not about whether momentum conservation applies. It was about an object no one had resolved and a pattern of activity no one had observed. One proposal imagined a body made largely of molecular hydrogen ice. Hydrogen ice is extraordinarily volatile. Gas from its sublimation could provide a strong push per unit mass and would be difficult to detect with the observations obtained in 2017. A hydrogen-rich iceberg could therefore appear inactive while accelerating. The attraction of the idea was clear. Its formation and survival were not. Molecular hydrogen freezes only at extremely low temperatures found in the coldest regions of molecular clouds. A macroscopic hydrogen body would be exposed to starlight, cosmic rays, interstellar gas, and the warming environment of the solar system. Critics calculated that it would erode too quickly or require implausible formation conditions. Refinements changed details of the thermal calculation, but pure hydrogen ice never became a broadly accepted identification. A different proposal replaced hydrogen with nitrogen. Pluto and Neptune's moon Triton have surfaces rich in nitrogen ice. Collisions in another planetary system might break fragments from an exo-Pluto. A shard dominated by nitrogen could be ejected into interstellar space, lose material as it approached the Sun, and accelerate without producing the ordinary water-rich signature expected from a comet. Nitrogen sublimation could also reshape the fragment. As layers were removed, a body that began less extreme might become flatter or more elongated. The hypothesis connected Oumuamua to familiar planetary chemistry. Its difficulty lay in population accounting. Producing enough nitrogen-rich fragments to make the first detected interstellar object likely may require a very large mass of Pluto-like surfaces to be excavated and ejected. Estimates differ because the number density of objects like Oumuamua is itself uncertain, but several studies found the required production demanding. The nitrogen model also depends on albedo, size, survival, and the efficiency of stripping crust from differentiated bodies. It remains an ingenious natural possibility, not a confirmed composition. Carbon monoxide ice, methane-rich material, and other volatile combinations have also been explored. Each can be adjusted to solve one part of the puzzle, and each meets constraints elsewhere. This pattern can make the scientific debate look like a collection of excuses. It is better understood as inverse reasoning from incomplete data. Astronomers knew the required momentum change. They knew what had not been detected. They searched for materials and structures capable of connecting the two. A particularly important proposal appeared in 2023. It did not require Oumuamua to be a pure hydrogen iceberg. Instead, It began with ordinary water-rich ice. During a long journey through interstellar space, energetic particles can penetrate an icy body. Radiation breaks some water molecules apart. Molecular hydrogen forms within the ice and can become trapped in pores or within the amorphous structure of the frozen water. When the object enters the solar system and warms, the ice changes internally. It anneals and reorganizes. The trapped hydrogen is released. Because hydrogen molecules are light and difficult to detect in the available observations, their escape can provide recoil without a bright dust coma or strong emission in the molecules that astronomers searched for. This radiolytic hydrogen model is different from a body built out of solid hydrogen. The bulk object can remain similar to a water-rich cometary planetesimal. The hydrogen is a product stored within it. Laboratory experiments have long shown that energetic processing of water ice produces hydrogen and that warming can release trapped gas across a range of temperatures. The model's authors calculated that a small body with dimensions consistent with Oumuamua could store and release enough hydrogen to explain much of the observed acceleration without extreme fine-tuning. The idea is attractive because it uses familiar material and a familiar interstellar process. It also does not turn the mystery into a solved fact. The internal structure of the actual object was unknown. Its original size was unknown. The depth to which radiation processed it depended on its travel history. The amount of hydrogen retained depended on temperature, porosity, ice structure, and erosion. Some researchers questioned whether the available processed layer could supply the required thrust for all plausible sizes and shapes. Others argued that the model naturally explains why an apparently inactive body behaved dynamically like a weak comet. As of 2026, radiolytically produced hydrogen trapped in water ice is one of the most discussed physically motivated natural explanations in the literature, but it remains actively debated. It is not a sample analysis. No instrument detected that hydrogen leaving Oumuamua. The distinction between a good explanation and a demonstrated explanation remains central. Another family of models changes density rather than chemistry. Imagine an object made of dust grains joined into an extremely porous aggregate. Its total size can be large while its mass remains low. Sunlight then produces more acceleration per unit mass. Gas flow or radiation pressure can move it without requiring a solid sheet. Very fluffy aggregates are expected in some early stages of planet formation. Collisions can compress or destroy them, but gentle growth in cold environments may create fractal structures with densities far below ordinary rock or ice. A porous body could also show little conventional outgassing if the acceleration came mainly from radiation pressure. The challenge is survival. A structure tenuous enough to be pushed strongly by sunlight must endure interstellar collisions, heating, rotation, and passage near the sun. Whether such an aggregate could remain intact depends on its scale, bonding, and thermal behavior. The proposal broadens the natural possibilities, but it does not provide a unique match. Radiation pressure itself is not speculative. Light carries momentum. Solar sails use this fact deliberately. When photons strike and reflect from a surface, they transfer momentum. The pressure is tiny, but it is continuous and declines with the intensity of sunlight. For a normal asteroid hundreds of meters across, radiation pressure is negligible compared with gravity because the object contains too much mass for its illuminated area. For a very thin sheet, the area-to-mass ratio can be much larger. In 2018, Shmuel Bialy and Avi Loeb calculated the area-to-mass ratio needed for sunlight to account for Oumuamua's acceleration. For a material density comparable to ordinary solids, the equivalent thickness would be below a millimeter, depending on the exact assumptions. A broad, thin object could behave like a light sail. That calculation was valid physics. The interpretation built on it became controversial. A naturally produced sheet roughly 100 meters wide and less than a millimeter thick would be difficult to form and preserve. An artificial sail, by contrast, is an object a technological civilization might intentionally construct. This led to the proposal that Oumuamua could be technology, an operating probe, an abandoned sail, or debris from an artificial structure. The possibility captured public attention because the object truly was interstellar and truly did have unexplained acceleration. But those two facts do not constitute evidence of engineering. An artificial hypothesis should make observations that distinguish it from natural alternatives. Oumuamua did not transmit a detected radio signal. Breakthrough Listen used the Green Bank telescope to search frequencies between about 1 and 12 gigahertz and found no narrowband emission associated with the object. The Allen Telescope Array and the Murchison Wide Field Array also reported null results in their searches. These observations were sensitive enough to exclude some low-power transmitters aimed broadly toward Earth. They did not exclude silent technology, a dead object, a narrow beam pointed elsewhere, communication outside the observed frequencies, or a transmitter active at another time. The null searches therefore weakened only specific technological scenarios. The motion also showed no clear maneuver. The additional acceleration was approximately radial and varied smoothly with distance, as a passive response to sunlight or heating might. There were no observed course corrections, no sudden turns, and no controlled approach to Earth. Its tumbling could be natural debris. It could also be damaged artificial debris. Again, the same data did not force a technological reading. The scientific objection to declaring an alien object was not that artificial interstellar probes are impossible. It was that natural small bodies already provide a broad and incompletely sampled family of explanations, while no observation uniquely indicated manufacture. The first detected member of any new population is especially dangerous to label anomalous. Before deep-sea exploration, the first unfamiliar fish could appear impossible. Before thousands of exoplanets were known, the first hot Jupiter seemed unlike the solar system. A population cannot be defined from one member. Oumuamua's oddness might reflect a rare composition. It might reflect selection bias. It might reflect the kinds of bodies easiest for pan-stars to detect. Or it might be a genuine outlier even among interstellar objects. The correct answer required more visitors. The second confirmed interstellar object arrived less than 2 years later. It was discovered in August of 2019 by the amateur astronomer Gennady Borisov. Its path was unmistakably hyperbolic, and it received the designation 2I Borisov. Borisov did not hide its nature. It possessed a coma. It grew a tail. Spectra revealed gases and dust released as sunlight warmed the nucleus. Carbon monoxide, water-related products, and other molecules placed it within the broad family of comets, though its chemistry also showed interesting differences from many solar system examples. Borisov was a comet from another planetary system. Its familiarity changed the meaning of Oumuamua. The first visitor had not established that all interstellar bodies were dry, inactive, red, and strangely shaped. The second showed that recognizable comets also move between stars. The difference could reflect composition. It could reflect evolutionary history. It could reflect how close each object passed to the Sun. Or it could reflect the way they were discovered. Borisov was found while still approaching perihelion, allowing months of observation as activity developed. Oumuamua was found after its closest solar passage, when any earlier display might already have declined. The comparison warned against treating the first object as a template. Then, in July of 2025, a third interstellar object was identified. The Atlas survey discovered it while it was still far from the Sun. It became 3I Atlas. Like Borisov, it was clearly cometary. It developed a coma, released gases, and was observed by a coordinated network of ground-based telescopes, space telescopes, and spacecraft. It passed perihelion in late October of 2025, remaining outside Earth's orbit and presenting no danger. By 2026, observations from instruments including Hubble, Webb, Sphere-X, TESS, Parker Solar Probe, and other missions had turned 3I Atlas into the most extensively observed interstellar comet yet. Its chemistry was not simply identical to one average solar system comet. Measurements found abundant volatile material, including carbon-bearing gases, water products, and methane. The ratios offered clues about formation in a cold environment and about the radiation and thermal history of the nucleus. Researchers continued refining those interpretations as the object departed. The third visitor supplied a new contrast. Oumuamua had been detected late, appeared inactive, and left a short, difficult dataset. Borisov and 3I Atlas were identified earlier and behaved as visible comets. This does not prove that Oumuamua was not cometary. It demonstrates that the word interstellar describes an orbit, not a single physical type. A fragment between stars can be an icy nucleus, a devolatilized crust, a collisional shard, a porous aggregate, or something not yet represented in the 3 confirmed detections. 3 objects are more informative than 1. They are still a tiny sample. To understand where Oumuamua came from, astronomers tried to reverse its path through the galaxy. At first, the direction appeared simple. Its incoming radiant lay in the general direction of the constellation Lyra, not far on the sky from the bright star Vega. Popular accounts sometimes transformed this into the claim that the object came from Vega. It did not. Vega is not located where it was when Oumuamua would have begun a long interstellar journey, and the reconstructed path did not point to a close, low-speed encounter that identified Vega as the source. A direction on the present sky is not a home address. Stars move. The sun moves. The gravitational field of the Milky Way curves trajectories over time. Passing stars perturb small bodies. Measurement uncertainty expands when a path is integrated backward for millions of years. The unknown non-gravitational force adds another uncertainty, because the exact past trajectory depends slightly on how that force behaved before and during the observed arc. Gaia transformed this search by measuring positions and motions for enormous numbers of stars. Researchers propagated candidate stellar orbits backward and compared them with the reconstructed path of Oumuamua. Several past encounters were identified. None was convincing enough to name a parent system. Some candidate stars passed within a fraction of a parsec of the path, but at relative speeds too high for an easy planetary ejection. Others had lower relative speeds, but larger encounter distances. The catalog itself did not include complete velocity information for every faint star and binary system the object might have passed. A true parent star may be absent from current data. It may have changed velocity through encounters. It may be a binary or a stellar remnant. The ejection might have happened so long ago that small errors now overwhelm the reconstruction. The honest conclusion is that the source system is unknown. Even the age of the journey is uncertain. Oumuamua's incoming velocity was close to the local standard of rest, a reference describing the average orbital motion of stars near the Sun around the Milky Way. This low peculiar velocity has been interpreted in 2 nearly opposite ways. One view says the object may have drifted for a long time until its motion became representative of the surrounding galactic population. Another argues that dynamically older objects tend to be stirred to larger random velocities through gravitational encounters, so remaining close to the local standard of rest may indicate a relatively young object. Neither inference is a clock. The velocity is one draw from a distribution. The ejection speed and direction matter. The parent star's motion matters. Galactic perturbations matter. An individual body can have a low relative velocity by chance at many ages. The red surface also cannot date the object precisely. Cosmic rays process only a limited depth. Erosion near the sun can remove irradiated material and expose fresher ice. Collisions with interstellar dust are rare but cumulative. A protective crust can form and later break. Oumuamua may have traveled for tens of millions, hundreds of millions, or perhaps billions of years. The data do not select one number with confidence. It is useful to imagine the journey without assigning a precise duration. The object leaves a planetary system. At first, the parent star is still the brightest source in its sky. Its gravity weakens with distance. Planets become points and then disappear. The object crosses the outer reservoir of comets and continues until the star no longer controls its trajectory. There is no sharp wall at the edge. The transition from one stellar system to interstellar space is gradual. Beyond the parent star's gravitational domain, the body enters the thin medium between stars. This space is not perfectly empty. It contains hydrogen, helium, dust grains, cosmic rays, magnetic fields, and photons from the galaxy. The density is extremely low. A cubic centimeter may contain roughly one atom in some regions and far fewer in others. Yet a journey lasting millions of years gives even weak processes time to alter a surface. Energetic particles penetrate ice. Ultraviolet light changes molecules. Dust grains strike at relative speeds of kilometers per second. Volatile molecules escape if the equilibrium temperature becomes high enough. The object passes through regions of different density and radiation. Most of the time, no star is close enough to look like a sun. The nearest lights remain points. Its internal temperature responds slowly. A small body can cool deeply, while occasional heating events affect the surface. If the interior contains amorphous ice, trapped gases can remain until later warming changes the structure. This quiet history is part of why the radiolytic hydrogen model is attractive. Interstellar travel is not merely empty waiting. It can manufacture and store molecules that become important during the next stellar encounter. How did the object escape in the first place? Planet formation naturally ejects material. A young system contains a disk of gas, dust, planetesimals, and growing planets. Gravitational encounters exchange energy. A small body passing near a massive planet can leave with a changed orbit. If the energy gain exceeds the binding energy to the star, the body escapes. Our own solar system probably expelled vast amounts of icy material while the giant planets migrated. Jupiter is especially efficient at ejection because it is massive and orbits far enough from the Sun that escape requires less additional speed than it does in the inner system. Other planetary systems contain giant planets on eccentric orbits, tightly packed planets, and architectures unlike ours. Their ejection rates can be high. Binary stars provide another mechanism. A planetesimal interacting with two moving stars can exchange energy more dramatically than it can with a single star. Material in unstable circumbinary or circumstellar regions may be thrown outward at substantial speed. Stellar evolution can unbind debris. When a star loses mass as a giant, the gravitational hold on distant objects weakens. Some escape. Close stellar encounters in clusters can strip comets and planetesimals from young systems. Tidal disruption can create fragments. A body passing close to a star, white dwarf, or giant planet can be stretched and broken. The pieces may emerge elongated, flattened, or compositionally unusual. Some models for Oumuamua invoke the tidal destruction of a larger object, leaving a shard that was later ejected. Collisions can excavate crust from differentiated worlds. That is the setting for nitrogen ice fragments from Pluto-like bodies. The existence of an interstellar object was therefore not surprising in theory. The surprise was how many must exist for pan-stars to have found one. A survey samples only a small effective volume for faint bodies hundreds of meters across. Detecting one implies a substantial number density, though the estimate spans orders of magnitude because it depends on size, brightness, survey efficiency, and the assumption that Oumuamua belongs to a common population. If objects of similar detectability fill interstellar space at the inferred density, planetary systems must eject enormous numbers of small bodies. This raised the mass budget challenge for specialized hypotheses. It is easier for the galaxy to supply abundant mixed ice and rock planetesimals than abundant thin artificial sails or fragments made specifically from the nitrogen crusts of exoplutos. But the detection process is biased. A bright high-albedo nitrogen fragment can be seen at a smaller size than a dark comet. A broad, thin object can present a large reflecting area for little mass. A population that is rare by mass may be overrepresented in a brightness-limited survey. One detection cannot determine the underlying distribution cleanly. The problem resembles hearing one footstep in a forest and estimating the number and species of all animals. The sound proves that something is there. It does not reveal the population without assumptions. The arrival direction also carried a statistical curiosity. Oumuamua approached from near the solar apex, the direction toward which the sun moves relative to nearby stars. An object nearly at rest in the local standard of rest is more likely to be encountered from this forward direction because the solar system moves into it. This geometry helped connect the low incoming velocity with the local stellar population. It did not imply targeting. A passive piece of debris can approach from the direction into which the sun is traveling for the same reason that raindrops strike the front of a moving car more often than the rear. Natural selection effects can create patterns that look intentional when described without the reference frame. The same caution applies to timing. Oumuamua passed through the solar system during the brief period when humans had surveys capable of finding it. That sounds extraordinary, but observers can only notice events during eras when observing is possible. If interstellar objects pass regularly, the first detection was always going to occur after the technology became sensitive enough. The encounter was fortunate. It was not evidence that the object arrived because telescopes existed. Still, the timing had emotional force. For almost all human history, an object of this size could cross the inner solar system without leaving any record. In 2017, automated software, digital detectors, rapid communication, and large telescopes converted a faint moving point into the first direct sample of a galactic population. No hand touched it, yet its path brought planetary science beyond the solar system. The weeks after discovery can be understood as an investigation conducted under a disappearing deadline. On the first nights, the essential task was orbital. Each image provided a position relative to background stars. The positions were sent to the Minor Planet Center, where observations of small bodies are collected and preliminary orbits are calculated. Other observatories searched the predicted location and extended the arc. As the orbit became hyperbolic beyond reasonable doubt, the designation changed. The International Astronomical Union introduced a new category, using the letter I for interstellar. The object became 1I 2017 U1. A new line had been added to astronomical naming because one moving point did not belong to any existing solar population. The next task was physical characterization. Brightness measurements were not identical because telescopes used different filters, observed at different times, and viewed the object under changing phase angles. Researchers had to combine these data while accounting for geometry. The brightness changed rapidly enough that a single exposure could catch the object near a maximum or minimum and give a misleading impression of its average size. Repeated monitoring revealed the large range and the failure of one simple period. Spectra were difficult because the target was faint. A spectrum spreads light into wavelengths. This allows composition to be inferred, but each wavelength channel receives fewer photons than a broad image. The available spectra were therefore low in detail. They showed a reddish continuum without strong gas features, not a complete inventory of the surface. Deep stacked images searched for a coma. Astronomers aligned many exposures on the moving object and added them. Background stars became trails or were removed, while any faint cloud traveling with Oumuamua would accumulate. The point spread profile was compared with stars. No extended dust was found. This was stronger than simply looking at one photograph and seeing nothing. It was still limited by particle size. Large grains close to the nucleus could remain unresolved. Very dark dust could be difficult to detect. Gas without dust would not necessarily produce a visible continuum coma. A narrow jet directed in an unfavorable geometry could escape detection. The absence of a coma was therefore a constraint on ordinary visible activity, not proof of a sealed surface. One can estimate the thrust from escaping gas with a simple idea. Momentum per second equals mass lost per second multiplied by the gas speed. To accelerate the nucleus, the gas carries momentum one way and the nucleus receives equal momentum the other way. For a heavy nucleus, more gas is needed. For a low-density nucleus, less is needed. For a volatile that leaves at high speed, less mass is needed than for a slower gas. This is why size and density uncertainty enters every proposed composition. Suppose the object was a compact, dark rock hundreds of meters long. The required mass loss could be substantial, making the lack of visible products difficult to explain. Suppose instead it was a smaller, bright, icy disk or a porous aggregate. The same acceleration could result from much less escaping mass. The astrometry measured acceleration per unit mass. It did not measure the mass. The direction of thrust also matters. A jet fixed to a rotating surface would point in changing directions. Over a full rotation, sideways components might cancel, while the average sunward or anti-sunward component remained. Thermal delay can shift peak activity away from the subsolar point. Multiple vents can combine. The measured acceleration was largely radial, but this does not require a perfectly centered engine. A tumbling nucleus with widespread weak release can produce a smooth average force even if the instantaneous jets are complicated. This possibility became more credible as astronomers identified objects in our own solar system that look inactive yet experience non-gravitational motion. They are sometimes called dark comets. The name does not mean that they are literally invisible or composed of dark matter. It refers to asteroid-like bodies without an obvious coma, whose trajectories contain accelerations suggestive of outgassing. By 2026, researchers had identified multiple examples and divided them into at least two broad groups. Some are small near-Earth objects with unusual acceleration components. Others are larger bodies on comet-like orbits. Their existence does not solve Oumuamua. It changes the comparison set. In 2017, an object with comet-like recoil and no visible activity seemed almost self-contradictory. Later discoveries showed that hidden or extremely weak activity can affect bodies that look inactive in images. In 2026, this principle gained a particularly clear example. A near-Earth object previously classified as inactive had already revealed a small non-gravitational acceleration in its orbit. Astronomers then obtained deeper images and detected a faint cometary tail. The motion had exposed activity before ordinary pictures did. This object was not a copy of Oumuamua, but it demonstrated that a trajectory can reveal weak outgassing hidden below an earlier imaging threshold. The solar system contains transitions between asteroid and comet. A body can lose most near-surface volatiles and retain deeper pockets. It can release gas with little dust. It can be active below the threshold of direct detection. Oumuamua may represent an interstellar version of this continuum. The dark comet analogy also has limits. The known objects do not duplicate its extreme hyperbolic orbit, shape constraints, and observing history. Their acceleration directions and sizes vary. A class can make a phenomenon less unique without making every member physically identical. This is how scientific context changes. A mystery sometimes becomes less mysterious not because new data arrive from the original object, but because other objects reveal that an apparently impossible combination occurs naturally. Oumuamua itself supplied no more photons. The universe supplied comparison cases. The solar heating it experienced was intense, but brief. At perihelion, the sunlight was roughly 16 times stronger than at Earth because the distance was about 1/4 of an astronomical unit. A dark surface facing the sun could reach high temperatures. The exact temperature depended on rotation, thermal inertia, reflectivity, and sublimation. If the body contained ordinary exposed water ice, vigorous activity might be expected. A radiation-processed mantle could insulate deeper layers. A tumbling motion would distribute heat differently from steady rotation. The surface may have cracked as volatiles escaped. The body might have lost a substantial fraction of its mass before discovery. This last possibility complicates every artist's reconstruction. The Oumuamua that entered the solar system need not have had the same dimensions or aspect ratio as the Oumuamua observed on the way out. Sublimation removes material from surfaces according to illumination. For some shapes and volatile distributions, erosion can increase elongation or flattening. A more ordinary fragment might emerge from perihelion looking extreme. Tidal forces from the sun were not strong enough at its perihelion distance to tear apart an ordinary compact body. The passage was inside Mercury's orbit, but far outside the solar Roche limit for most plausible materials. A sub-millimeter artificial sheet would face different structural issues, but even there, claims that it must have been destroyed depend on material strength, orientation, and thermal properties. The observed survival therefore rules out some fragile configurations, but not every thin or porous model. No fragmentation was seen. There was no train of pieces and no sudden brightness event clearly indicating breakup. The complex light curve can be explained by one tumbling body. The object may have possessed small unseen fragments, but the astrometry did not require them. Solar wind was considered as a force. Charged particles streaming from the sun transfer momentum. For the solar wind to create the observed acceleration without other signatures, Oumuamua would need unusual magnetic or electrical properties. Detailed analysis found this less plausible than outgassing. Interaction with interplanetary dust or gas was also too weak. A cloud of separated fragments whose center of light shifted relative to its center of mass was examined and did not explain the full pattern. Thermal radiation can create recoil, as seen in spacecraft through the Yarkovsky effect and in the Pioneer anomaly's eventual explanation. For a small body, an isotropic heat emission can alter an orbit slowly. The magnitude and direction for Oumuamua were not an easy match without extreme properties. Radiation pressure remained possible only for a high area to mass ratio. Outgassing remained possible only with activity below detection or unusual volatiles. The data did not allow the force to be labeled by motion alone. This is an important feature of inverse problems. Different mechanisms can generate nearly the same trajectory. A radial push decreasing with distance can come from photons or from gas released by solar heating. Both ultimately depend on sunlight. Astrometry measures the response, not the microscopic carrier of momentum. To distinguish them, one wants additional observables: a gas spectrum, a dust tail, a change in rotation, a thermal detection, a resolved shape, a polarization signature, a direct sample. For Oumuamua, Each of these was absent, limited, or ambiguous. The mystery was not created by one impossible observation. It was created by the failure to collect enough independent kinds of evidence before the object faded. That is why arguments can continue years after departure. The dataset is fixed. New laboratory results and new models can be applied to it, but no theory can request a better exposure from 2017. The observation window cannot be reopened. This makes the case scientifically valuable in a different way. It tests how conclusions should be drawn when evidence is real, sparse, and permanently incomplete. A weak explanation can be made to fit by adding assumptions. A strong explanation fits multiple constraints with assumptions that are independently plausible. The radiolytic hydrogen model gains strength from laboratory ice physics and from the natural expectation of irradiated water-rich planetesimals, while published criticism questions whether enough hydrogen could be produced, retained, and released under every plausible thermal history. The nitrogen model gains strength from known nitrogen-covered worlds, but loses strength in production estimates. The light sail model gains strength from the well-understood inverse square behavior of photon pressure, but requires an extreme area to mass ratio and offers no independent sign of manufacture. No numerical score accepted by the whole field ranks them. Scientific consensus in such a case is not a vote naming one winner. It is a distribution of confidence. Most planetary scientists consider a natural origin overwhelmingly more plausible than technology. Many favor some form of hidden outgassing. They differ on the molecule, structure, and detailed thermal history. Some regard the available data as insufficient to choose even among broad natural classes. A small number argue that the artificial possibility deserves greater weight. The disagreement is real. It is not symmetrical. An idea can be discussed in scientific literature without being equally supported. The same distinction applies to the phrase unexplained acceleration. Unexplained does not mean inexplicable by nature. It means no explanation has been directly verified and accepted as uniquely satisfying all available constraints. There is a large distance between those statements. That distance is where Oumuamua has remained. The artificial origin proposal deserves careful treatment because dismissing it too quickly and embracing it too quickly are mirror image errors. Technology exists in the universe. Human beings have already placed artificial objects on trajectories that leave the solar system. Pioneer 10 and 11, Voyager 1 and 2, and New Horizons are moving outward. Their shapes, densities, rotations, radio emissions, and thermal properties differ from natural asteroids. A distant observer finding one of them would be correct to consider manufacture. It is therefore scientifically legitimate to ask whether an interstellar object could be technological. The question is not forbidden. The evidence must do the work. A solar sail has a recognizable dynamical principle. It gains momentum from starlight without expelling propellant. A sail can accelerate radially away from a star and follow an inverse square law. If Oumuamua had a sufficiently low mass per unit area, the measured trajectory could be reproduced. But an area-to-mass ratio does not identify an object uniquely. A very thin solid sheet has one such ratio. A highly porous aggregate can have another. A broad fragment with low density can respond strongly. Outgassing can mimic the same distance dependence. The calculation shows what properties radiation pressure would require. It does not show that those properties were measured. The thickness often quoted in public discussions assumes a compact material density and a flat geometry. Change the density and the equivalent thickness changes. Change the shape and orientation and the effective illuminated area changes. The word millimeter is therefore a model consequence, not a telescope measurement. The sail interpretation also faces the light curve. A flat reflective sheet tumbling through sunlight can produce dramatic brightness changes. Yet the observed color was red rather than highly metallic, and no sharp specular flashes were identified. A weathered or coated sail could avoid those expectations, but every added possibility reduces the power of prediction. An operating probe might stabilize itself or navigate. Oumuamua tumbled. A dead sail or fragment could tumble naturally. An intentional flyby probe might approach a planet, transmit, or alter course. Oumuamua passed through on a hyperbolic path that did not target Earth closely and displayed only a smooth, weak acceleration. An alien technology could be silent and unguided. That possibility is impossible to exclude completely. It is also difficult to test. A hypothesis that can accommodate every observation by allowing the object to be active or dead, transmitting or silent, controlled or uncontrolled, reflective or coated, becomes flexible enough to survive without gaining support. Good hypotheses risk failure. They tell observers what should be seen next. For Oumuamua, the artificial suggestion did produce useful actions. Radio telescopes searched. Researchers considered infrared waste heat, unusual reflection, and dynamics. The searches returned no positive technosignature. That outcome does not prove nature, but it leaves the technological case dependent mainly on interpreting the acceleration and inferred geometry as too unusual for natural bodies. Natural bodies, however, had barely been sampled in interstellar space. This is where prior probability enters, even if the phrase is never spoken. Planetary systems are known to form and eject debris. The galaxy must contain natural rocks and ices between stars. Technological civilizations capable of producing large interstellar artifacts are not known to exist, though they may. Before examining the details, a random interstellar minor body is therefore more likely to be natural under the evidence currently available. An artificial explanation can overcome that lower prior probability only with distinctive evidence. A structured signal would do so. Resolved manufactured geometry might. Controlled acceleration inconsistent with passive forces might. Materials with impossible natural spectra might. Oumuamua provided none of these. Its strongest anomalies had plausible natural pathways, even if no pathway was confirmed. This is why most specialists did not regard the artificial idea as the leading explanation. The media environment changed the apparent balance. A phrase such as invisible hydrogen released from radiation-processed amorphous water ice is accurate but difficult to place in a headline. Alien probe is immediate. The most dramatic explanation received attention far beyond its share of support. As coverage repeated the story, many people encountered the technological claim before learning the underlying measurements. The cigar-shaped artwork became visually associated with a spacecraft even though the elongated shape itself was uncertain. This created two myths. The first myth said scientists had detected an alien vessel and were refusing to admit it. The second said the alien idea was invented without any scientific calculation. Neither was correct. The proposal began from a real measured acceleration and a valid radiation pressure calculation. It then made an interpretation that most researchers considered unnecessary and weakly supported. Science can contain a legitimate minority hypothesis without treating it as equally probable. The controversy also revealed how the phrase "extraordinary claims require extraordinary evidence" can be misunderstood. It does not mean unusual ideas should be ignored. It means the evidence must be able to distinguish the extraordinary idea from less extraordinary alternatives. A small trajectory anomaly with multiple passive explanations does not reach that level. The absence of a conventional coma raises the interest. It does not supply a transmitter. The radio observations themselves deserve perspective. A transmitter on or near Oumuamua could have been very weak and still detectable during the closest observations if it radiated isotropically in the searched narrow bands. Breakthrough Listen reported no candidates that followed the object. Other arrays found no associated emission. Human spacecraft do not radiate continuously across all frequencies. They send narrow beams toward known receivers. A probe designed by an unknown civilization could use optical pulses, broad-spectrum signals, neutrinos, methods unknown to us, or no communication at all. Thus, a radio null result is not a universal test of technology. It is evidence against a subset of simple transmitting scenarios. The same limitation applies whenever SETI searches a target. Silence constrains engineering choices. It does not constrain imagination. This asymmetry makes positive identification difficult. Natural origin can be supported by showing that known physical processes reproduce the data with plausible materials. Artificial origin requires a sign that nature is unlikely to produce. The 2023 trapped hydrogen model moved the debate by making a hidden cometary force less contrived. It did not prove the model, but it reduced the need to invoke a manufactured sail simply because common gases were not detected. The later recognition of dark comets had a similar effect. Every natural comparison object changes what counts as extraordinary. Suppose future surveys find many small interstellar bodies with radial accelerations and no visible coma. Then Oumuamua becomes the first member of a class. Suppose instead every later object is a conventional active comet and none shares its behavior. Then it remains an outlier, and rare explanations gain relative interest. Suppose one future object is detected inbound and followed continuously. Astronomers measure its gas, temperature, rotation, and acceleration together. If radiolytic hydrogen predicts the observations accurately, the Oumuamua case gains an analog. Suppose a future object changes course toward a planet. Then an entirely different level of investigation begins. The correct response to uncertainty is not permanent indecision. It is better observation of the next opportunity. This is why Oumuamua's greatest scientific consequence may not be the answer to what it was. It may be the system built to ensure that the next visitor does not escape with the same questions. The next opportunity is no longer left to the same survey system that happened to find the first. On June 30th, 2026, the Vera Rubin Observatory officially began the legacy survey of space and time. From Cerro Pachón in Chile, its wide-field telescope now photographs large areas of the southern sky night after night. The camera contains billions of pixels. The survey revisits the same regions repeatedly, allowing software to identify points that move, brighten, fade, or appear for the first time. Rubin was not built only for interstellar objects. It will study dark matter, dark energy, variable stars, supernovae, galaxies, asteroids, and the evolving sky. Its design is nevertheless unusually well suited to finding visitors between stars. Pan-stars discovered Oumuamua after perihelion because the object was faint and approached from a difficult direction. Rubin can search deeper and cover a broad field quickly. Repeated images allow motion to be identified sooner. Its alert system can inform astronomers around the world rapidly enough for other telescopes to begin follow-up. Predictions for the number of interstellar discoveries remain uncertain because the population is uncertain. Rubin may find several over its survey, perhaps many more if small objects are abundant and bright enough. Its first years should begin testing estimates derived from Oumuamua, Borisov, and 3I Atlas. The goal is not merely a larger count. It is earlier warning. An object discovered while still inbound offers information that 2017 could not provide. Astronomers can measure its brightness before solar heating becomes strong. They can watch the onset of activity. They can compare the inbound and outbound accelerations. They can determine whether gases appear at particular temperatures. They can monitor changes in rotation. They can observe perihelion rather than reconstruct it afterward. A long arc also improves the original incoming trajectory, making a search for the parent system less uncertain. The ideal discovery would occur far beyond Jupiter. At those distances, the object would be faint, but its pristine surface and low activity would be scientifically valuable. Space telescopes could measure carbon dioxide, carbon monoxide, water, methane, and other species inaccessible or difficult from the ground. As it approached, observatories could prepare rather than improvise. The sequence of measurements would become an experiment. If acceleration began before water ice should sublimate, more volatile gases would be suspected. If acceleration appeared without any detected species despite deep spectroscopy, radiation pressure and hidden gas models would gain interest. If the spin changed with the force, jets would be implicated. If the force followed illumination while the object's projected area changed, a low-density or sail-like structure could be tested. The missing pieces from Oumuamua define the observing plan for its successors. Discovery alone is not enough. Coordination determines whether a brief visitor becomes a physical object rather than an orbital mystery. The response to 3I Atlas demonstrated this new approach. Because it was found months before perihelion, observatories and spacecraft could schedule observations across wavelengths. Multiple missions viewed the coma from different locations. Webb measured infrared molecules after the comet had been warmed. Tests devoted continuous photometry. Hubble constrained the nucleus. Solar missions observed the object from geometries unavailable to Earth. The result was not one perfect answer. It was a layered dataset in which chemistry, activity, rotation, size, and trajectory could be compared. Oumuamua lacked that layering. The difference between the first and third visitors was less than a decade of technological readiness. A spacecraft encounter would provide another leap. Reaching an interstellar object is difficult because discovery often occurs late and the target moves rapidly on an unbound path. A spacecraft launched after the announcement must gain enough speed and meet a trajectory that was not known when the mission was designed. Conventional planetary missions spend years using gravity assists and carefully planned windows. An interstellar visitor does not wait. One response is to prepare a spacecraft before the target exists. The European Space Agency's Comet Interceptor mission is being developed for launch in the late 2020s. After launch, the spacecraft is intended to wait near the Sun-Earth L2 region until a suitable target appears. Its primary goal is a dynamically new comet arriving from the distant Oort cloud, but an accessible interstellar object could be considered. The mission consists of a main spacecraft and 2 probes designed to separate before the encounter. Observations from multiple paths would create a 3-dimensional view of the gas, dust, plasma, magnetic environment, and nucleus. An interstellar target is less likely than an Oort cloud comet because the geometry must be reachable with the available propulsion and waiting time. The design still represents a change in philosophy. Instead of choosing a known comet and building a mission around its orbit, the spacecraft waits for the sky to provide the destination. Future interceptors could be optimized specifically for interstellar objects. They might wait at strategic locations with propulsion reserved for rapid departure. Several smaller spacecraft could be prepared so that one has a favorable geometry. Solar sails or high-energy stages could increase the reachable set. A flyby would be fast. At tens of kilometers per second, the closest encounter might last minutes. Cameras would need to find and track a small dark nucleus autonomously. Dust impacts could be dangerous. Instruments would collect spectra, images, fields, particles, and perhaps the mass of grains crossing detectors. Even a brief flyby could answer questions that years of modeling cannot. Is the nucleus compact or porous? Does it contain layered ice? What gases leave the surface? Is the shape truly flat or elongated? Are there pits, fractures, jets, or manufactured regularity? What isotopic ratios reveal its birthplace? A return sample would be far harder, requiring not only catching the object, but matching its speed, collecting material, and returning to Earth. A dust collector passing through the coma of an active interstellar comet may be more achievable than landing on a small tumbling nucleus. There have also been engineering studies asking whether Oumuamua itself could still be reached. The answer is not simply no. Concept studies under the name Project Lyra have explored trajectories using Jupiter encounters, high-energy rocket burns, and close solar passages. Some calculations find technically conceivable launches in the 2030s followed by journeys lasting decades. Conceivable is not approved. No such mission has been selected or funded. The spacecraft would need to overtake an object with a heliocentric excess speed above 26 kilometers per second by the time of encounter. Both would be extremely far from the Sun. Navigation toward a small dark target whose present position depends on accumulated orbital uncertainty would be demanding. Communication and power would resemble or exceed outer solar system missions. A high-speed flyby after decades might return limited data unless the spacecraft could locate the target precisely and operate in very low light. The idea remains an engineering study rather than a rescue plan. This corrects another common statement. Oumuamua is not beyond every trajectory allowed by physics. It is beyond any easy, existing, or currently approved follow-up. The distinction reflects the difference between capability and principle and a mission that societies actually choose to build. By August of 2026, Oumuamua has traveled to roughly 50 astronomical units from the Sun, far beyond Neptune's orbit, but still well inside the heliosphere. It is far too faint for direct optical tracking. Its predicted path continues from the last measured orbit. The uncertainty region slowly grows. The body itself continues tumbling, unless weak torques have changed it. Sunlight is now far weaker. Any water-driven or hydrogen release activity should have faded. Its surface cools toward interstellar conditions. The solar encounter becomes one brief thermal event in a much longer journey. The object will not return. Its hyperbolic orbit is open. The Sun changed its direction and temporarily increased its speed, but the departure carries it back into the galactic population from which it came. Ahead lie other stars, but space is vast. A close encounter with another planetary system is unlikely on human timescales. The body may travel for millions of years before passing meaningfully near a star. It may never enter another interplanetary system before galactic perturbations change its path. The next observers, if any exist, may not see the same object we inferred. Solar heating may have removed volatile layers. Radiation will process the surface again. Dust impacts will add tiny craters. The tumbling can persist. Oumuamua is not a message sealed against time. It is material undergoing a history. The Hawaiian name calls it a messenger, but the message is not an intentional sentence. It is carried in motion, composition, shape, and damage. We received only part of it. The phrase first visitor from another star system can suggest that the solar system had been isolated until 2017. It had not. Interstellar dust enters constantly. Neutral atoms from the local interstellar cloud flow through the heliosphere. Cosmic rays arrive from distant energetic events. Some meteors may travel on interstellar trajectories, though proving their origin is difficult because atmospheric measurements and small velocity errors can turn a bound orbit into an apparently unbound one. What changed with Oumuamua was scale and certainty. This was a macroscopic body observed before it reached Earth's atmosphere, tracked long enough to establish an incoming hyperbolic orbit that planetary scattering could not explain. It was a piece of another planetary system large enough to have geology in the broadest sense. It could possess layers, pores, fractures, radiation crust, and an internal thermal history. That makes interstellar objects a new method for studying exoplanetary material. Ordinary exoplanet observations measure light. A planet passes in front of a star, slightly reducing its brightness. A spectrum reveals atmospheric molecules. A star's motion reveals the gravitational influence of unseen worlds. Direct images separate a few young giant planets from their stars. Interstellar objects bring solid material from those systems into our neighborhood. Even without a sample, their gases and dust can reveal isotopes and chemistry. A spacecraft encounter could inspect surfaces formed under another sun. This is not exactly a free sample delivery. The object has been altered during ejection and travel. Its surface is not a pristine label from one known world, yet it contains information unavailable from a distant point of light. Borisov and 3I Atlas showed that familiar molecules exist in comets formed elsewhere. Their differences showed that familiar does not mean identical. Oumuamua added a more difficult lesson. Planetary systems may produce bodies outside the categories established from our own neighborhood. Or familiar bodies may appear unfamiliar when observed briefly and under poor geometry. Those two possibilities are easy to confuse. A strange dataset can mean a strange object. It can also mean an ordinary object viewed incompletely. The large brightness variation illustrates this. If Oumuamua had been resolved, shape would not dominate the debate in the same way. A few images could distinguish a flattened shard from a long spindle, reveal albedo patches, and measure the rotation axis. Because it remained a point, many properties became entangled. The same is true of exoplanets. Astronomy often studies objects that cannot be touched or resolved. Researchers infer hidden properties by combining weak signals with physical models. The models are powerful because the laws of light, motion, and thermodynamics are universal. They remain conditional because several hidden structures can produce the same data. Oumuamua is therefore not an embarrassment for astronomy. It is a concentrated example of how astronomy works. The orbit was secure because many positions over time constrain motion tightly. The tumbling was secure because no single period reproduced the light curve. The extreme brightness range was secure because it appeared repeatedly. The exact shape was conditional because brightness does not map uniquely to geometry. The absence of a visible coma was secure within the sensitivity of the images. The absence of all outgassing was not secure because some gases and low levels of activity could remain unseen. The acceleration was secure. Its mechanism was not. This hierarchy should be preserved whenever the story is told. Without it, uncertainty spreads backward and makes everything seem doubtful. Or speculation spreads forward and makes every possibility sound measured. Neither reflects the evidence. The origin of the name also carries a useful nuance. Oumuamua is sometimes translated simply as scout. A scout implies intention. The fuller sense of a messenger or distant arrival does not require that the object was sent. Human language assigns agency easily. We say a comet visits, a planet captures, a star dies, a galaxy eats another galaxy. These verbs help create a mental picture. They do not change debris into a traveler with a destination. The object entered because its galactic path and the sun's path happened to cross. The sun gravitationally focused the trajectory. From far away, the effective cross-section for encounters is larger than the physical size of the inner solar system because solar gravity bends passing objects inward. The probability was still small for any particular fragment. The population was enormous. Given enough fragments and enough time, rare passages become expected. The solar system should contain interstellar objects at large distances more often than surveys detect them. Most are too small and dark. Some pass far from the sun. Some approach from the daytime sky. Some move through regions not covered deeply enough. Detection is the narrow filter. This has consequences for interpreting the first sample. Pan-STARRS was more likely to find an object that passed near Earth, reflected enough light, and moved into searchable sky. Brightness depends on albedo and projected area. An unusual broad object may be overrepresented. Oumuamua's detectability might be connected to its shape. If it was a flat body presenting a large area at times, its peaks made it visible. A more spherical object with the same mass might have remained below the threshold. The first object found need not be the most common. It may be the object that wins the selection lottery. The third object, 3I Atlas, appears to have been substantially larger and more active than Oumuamua. It was visible farther away. Borisov also displayed a coma that increased its reflecting area. This helps explain why confirmed detections can differ greatly. A survey detects light, not census categories. Rubin's deeper repeated search will make the filter wider. As the sample grows, astronomers can infer a size distribution. They can compare active and inactive fractions. They can test whether incoming velocities match known stellar populations. They can search for preferred compositions and ages. They can estimate how efficiently different kinds of planetary systems eject material. 100 interstellar objects would transform the field. 1,000 would reveal subpopulations. One object created hypotheses. A population can eliminate them. The number density inferred from Oumuamua also touches the history of planet formation across the galaxy. If small bodies are abundant between stars, then ejection is not an occasional accident. It is a common outcome of building planets. Every mature system may be surrounded by an invisible wake of lost material. The Sun itself has contributed. During the migration of the giant planets, enormous numbers of icy planetesimals were scattered. Some entered the Oort cloud. Some collided. Some escaped. Those solar fragments now travel elsewhere. A future observer around another star might detect one of them and call it a visitor from the direction of our former position. It would not carry a label. Its isotopic composition might resemble solar system comets. Its trajectory, integrated backward through millions of years, might fail to identify the Sun. It could become another mystery. Oumuamua therefore reverses the usual image of planetary systems as closed families. Stars exchange debris without exchanging planets. The galaxy contains a slow circulation of discarded solids. Most never enter another system deeply. A few pass close enough to be heated, observed, or captured. Capture is possible, but rare. To become permanently bound, an interstellar object must lose energy. The Sun alone cannot capture it through a simple two-body encounter because gravity accelerates it inward and removes the same energy on the way out. Interaction with a planet, a binary companion, gas, or fragmentation can change the energy. Young planetary systems with gas disks may capture interstellar planetesimals more efficiently. Such captured seeds could participate in planet formation. Material from one system might become embedded in another. This possibility does not imply that life or complex chemistry commonly travels that way. It shows that the boundaries between systems are dynamically permeable. Oumuamua passed through without capture. The Sun redirected it. The planets barely affected the outcome. For a few months, a fragment of unknown origin moved through the same region as human spacecraft and the worlds of the inner solar system. Then the geometry separated them again. The encounter was brief because speed and scale made it brief. The scientific consequences are lasting because first detections change what observers prepare to see. Several complete histories can be built for Oumuamua. They begin in different places and end with nearly the same measured points of light. In one history, the object forms in the cold outer disk of an ordinary planetary system. Dust and ice collide gently. The body grows porous with water-rich ice, carbon-bearing compounds, and trapped volatile molecules. giant planets later destabilize its orbit. A close encounter provides enough energy to escape. During interstellar travel, cosmic rays process the outer meters or decimeters depending on energy and time. Water molecules break apart. Hydrogen accumulates in the amorphous ice. The surface darkens and reddens. The object may collide with smaller grains and begin tumbling. Millions of years later, it enters the solar system. Solar warming reorganizes the ice and releases stored hydrogen. The gas escapes without carrying much dust. The recoil produces the measured acceleration. Sublimation and erosion alter the shape. By the time telescopes detect it, the activity is too weak or too spectrally elusive to reveal a coma. This is the radiolytic hydrogen history. It requires no rare planetary crust and no technology. Its unobserved step is the actual hydrogen inventory. In another history, the object begins as part of the surface of a Pluto-like world. The planet or dwarf planet differentiates. Nitrogen freezes onto the crust. Later collisions excavate bright nitrogen-rich fragments. A giant planet or binary star ejects one. The fragment crosses interstellar space and loses material slowly. Near the Sun, nitrogen sublimation drives acceleration. Erosion makes the remnant flatter. Because nitrogen gas was not directly constrained as strongly as common comet species, the body appears inactive. This is the nitrogen shard history. It explains the force with a volatile known on solar system worlds. Its difficulty is producing enough such fragments and preserving them long enough for one to be detected. In a third history, the object is not compositionally rare. It is structurally rare. It grows as a fractal aggregate of dust and ice, so porous that most of its volume is empty. Its area is large compared with its mass. Solar radiation pressure pushes it measurably. The aggregate survives because its low internal stresses and distributed structure respond differently from a thin solid sheet. This is the dust bunny history. It avoids invisible gas. Its challenge is demonstrating that such a large, extremely low-density structure can survive ejection, interstellar impacts, solar heating, and tumbling. In a fourth history, a larger rocky or icy body passes close to a star or compact object. Tidal forces stretch and break it. A fragment leaves with an extreme aspect ratio. Later heating drives weak outgassing from buried volatiles. The odd shape and acceleration come from separate natural events. This is the disrupted fragment history. It uses well-known gravitational physics. Its challenge is finding a sequence that produces the inferred geometry, population abundance, and surviving volatile content without excessive fine-tuning. In a fifth history, a technological civilization builds a thin sail. The sail crosses interstellar space intentionally or as debris. It no longer operates. Its low mass per area allows sunlight to accelerate it. Damage and long travel leave a reddish surface. The sheet tumbles because control has failed. This is the artificial debris history. It reproduces radiation pressure dynamics directly. Its challenge is that none of the observations independently reveal manufacture, and the existence and abundance of such artifacts are unknown. These histories cannot all describe the same object. They can all be narrated around the existing evidence because the evidence is sparse. A useful comparison asks what each history predicts beyond the facts used to construct it. The radiolytic hydrogen model predicts that future water-rich interstellar bodies exposed to cosmic rays may release hydrogen over characteristic temperature ranges. Early infrared and ultraviolet observations, combined with precise acceleration and thermal modeling, could test that behavior. The nitrogen model predicts high albedo and nitrogen-dominated gas, as well as a connection with populations of differentiated icy worlds. A future fragment observed inbound could reveal nitrogen directly and show whether its shape evolves through sublimation. The porous aggregate model predicts low density, unusual response to radiation pressure, and possibly distinctive polarization or thermal properties. The tidal fragment model predicts families of shapes and ejection velocities connected with close stellar encounters. The artificial model predicts nothing unavoidable if the object is dead debris, but particular versions may predict flat geometry, unusual materials, reflected light behavior, or technological emissions. This last point is why dead artifact hypotheses are scientifically difficult. A living probe can be tested through action. A dead object can resemble nature after enough damage and time. Absence of evidence then becomes easy to explain. The hypothesis may remain possible while providing little guidance. One can also compare how much unseen structure each explanation requires. Every model contains invisible details because the object was unresolved. Natural models require ice phases, porosity, volatile distributions, or erosion histories. The artificial model requires a civilization, manufacturing, ejection, survival, and the absence of a distinctive signal. Parsimony is not simply counting words. It asks which assumptions connect with processes independently known to occur. Water ice, cosmic rays, cometary recoil, collisions, and planetary ejection are observed or strongly established. Interstellar sails are physically possible, but not observed outside human technology. This gives natural models an evidential advantage even before one is selected. The mystery remains because advantage is not identification. A court can know that an unknown animal probably made a track without knowing the species. Astronomy can know that passive natural physics probably moved Oumuamua without knowing the molecule or structure. The distinction is satisfying only if uncertainty is treated as a result rather than a failure. Some questions do not have enough preserved information for one answer. The object has left. The spectra were limited. The shape was unresolved. The most rigorous conclusion may remain a probability distribution. This is common in historical sciences. Geologists reconstruct an ancient eruption from ash layers. Paleontologists infer an animal from fragments. Cosmologists infer early conditions from radiation altered over billions of years. The event cannot be repeated. Evidence can still favor explanations without selecting one perfectly. Oumuamua is a historical event in celestial mechanics. The Sun performed one uncontrolled experiment on an unknown sample. Humanity noticed after the strongest heating had occurred. The apparatus was the solar system. The measurements began late. The sample departed. From this perspective, the debate becomes calmer. No theory needs to win for the encounter to be valuable. The object established that detectable interstellar planetesimals exist. It showed that at least one can appear inactive while experiencing measurable non-gravitational acceleration. It forced models of ejection populations to confront a real number density. It inspired technosignature searches and rapid response mission concepts. It changed survey priorities. It gave later objects a new designation system and a prepared scientific community. Borisov and 3I Atlas were not merely second and third curiosities. They were observed in a field that Oumuamua had created. Even the errors in early public images had consequences. The cigar became so memorable that later analyses of a disc-like shape had to correct a picture rather than merely update a parameter. This reveals the power of visualization in science communication. An artist must draw something. A point of light is accurate but emotionally empty. A long reddish object communicates the inference, then quietly hardens into supposed observation. The same can happen with a flat sail. Once drawn, a hypothesis acquires a visible surface, shadows, edges, and apparent reality. The actual dataset remains pixels and numbers. A careful mental image should therefore remain changeable. At one moment, imagine a dark tumbling shard. At another, a flattened icy fragment. Then let both dissolve back into an unresolved point. That point is closer to what the telescopes saw. Its mystery is not weakened by refusing to give it a definite outline. It becomes more honest. The true object possessed one shape. The human record did not preserve it. At this stage, the evidence can be arranged in layers of confidence. What was Oumuamua? It was the first confirmed interstellar object detected while passing through the solar system. That answer is certain. It was a small body on an unbound orbit, reddish in broad color, showing a large brightness variation and a complex tumbling rotation. That answer is strongly supported. It experienced a weak outward non-gravitational acceleration during the observed outbound arc. That answer is also strongly supported. It was probably a natural planetesimal fragment with hidden or unusual cometary activity. That answer expresses the balance of current scientific judgment. It was specifically a water-rich body releasing radiolytically produced hydrogen. That answer is a leading physical model, not a direct detection. It was a nitrogen shard, porous aggregate, tidally disrupted fragment, or artificial sail. Those answers remain proposals with different difficulties and levels of support. The hierarchy is more informative than one dramatic label. The phrase first visitor can also be answered more carefully. Oumuamua was first in discovery order. It was not necessarily the first interstellar body ever to enter the solar system. Countless others almost certainly passed before human observers existed. Some may have struck planets or the sun. Some may remain captured on difficult-to-identify orbits. Some may have crossed during the early solar system when gas and crowded planetary dynamics made capture more likely. The number 1 in 1I belongs to a catalog, not to cosmic history. The same is true of the mystery. It was the first time humans faced this exact combination of evidence. Nature had no obligation to make the first object representative. A field that begins with an outlier can spend years confusing individual properties with population properties. Borisov corrected part of that error. 3I Atlas corrected more. Future Rubin discoveries will continue the process. The 3 known objects already suggest diversity. Oumuamua was small, late discovered, apparently inactive, and dynamically puzzling. Borisov was an active comet with a clear tail and chemistry that could be compared with solar system comets. 3I Atlas was discovered much farther out, larger and vigorously active, allowing an unprecedented multi-mission campaign. There is no single visual form called an interstellar object. The category may eventually include dormant rocky fragments, icy comets, differentiated crustal shards, rubble piles, and bodies modified by ages of radiation. The galaxy's debris should reflect the diversity of planetary systems. Some stars are metal-rich. Some disks contain more carbon or water. Some systems form giant planets early. Some contain close binaries. Some experience violent scattering. The objects they eject carry those histories in proportions that surveys may one day measure. A statistically large sample could answer questions far beyond Oumuamua. How common are Pluto-like worlds? How often do giant planets eject comets? Do binary systems dominate the fastest interstellar bodies? Are most objects ancient or recently expelled? Do cosmic rays create similar crusts on different compositions? How often does hidden activity occur? Do any bodies contain complex organic molecules unlike those in the solar system? The first visitor opened these questions because it transformed hypothetical debris into an observed population. Its acceleration also changed the way small forces are regarded. Orbital motion is not only gravity. For small bodies, sunlight, thermal emission, outgassing, and particle interactions can accumulate into measurable changes. These effects reveal physical properties when interpreted carefully. A trajectory can function as a remote balance scale. If the force is known, acceleration constrains mass per area. If mass and shape are known, acceleration constrains gas production. For Oumuamua, too many variables were unknown for the scale to yield one reading. For future objects, simultaneous observations may close the system of equations. This is one reason astrometry is as valuable as a beautiful image. A spectrum can identify molecules. A trajectory can reveal invisible mass loss. A light curve can reveal rotation. Each measurement is incomplete alone. Together, they create a physical body. The 2017 campaign assembled only part of that body. The missing parts became exaggerated in public imagination because the known parts were so unusual. There is another reason the case persists. The object cannot answer back. A disputed exoplanet atmosphere can be observed during another transit. A variable star can be monitored through another cycle. An asteroid can return near Earth. Oumuamua offers no second observing season. The debate therefore evolves through theory, analogs, and reanalysis rather than new direct data. The original astrometry can be recalibrated. The light curve can be modeled with new shapes. Laboratory ice experiments can test hydrogen production. New dark comets can show hidden acceleration. But no one can ask Oumuamua to turn slightly so that a camera sees its broad face. Permanence gives some astronomical mysteries time to shrink. Departure preserves this one. Even so, the mystery has changed since 2017. At first, the object was described as a dry interstellar asteroid. Then the non-gravitational acceleration made a cometary force likely. The absence of visible activity made that comet unusual. The sail proposal moved public discussion toward technology. Nitrogen and hydrogen ice models explored exotic volatiles. The trapped hydrogen model returned attention to a water-rich comet altered by interstellar radiation. Dark comets provided local analogs for inactive appearance with dynamical recoil. The sequence has moved from astonishment toward physical context. A mystery can become more ordinary without becoming solved. This is often how science progresses, but before the broader meaning of the encounter can be carried toward the ending, several familiar descriptions of its motion need to be made exact. Several common descriptions of the encounter become clearer when the orbit is separated from the extra acceleration. Oumuamua accelerated as it approached the Sun. Gravity did that. It reached its greatest heliocentric speed near perihelion. As it moved outward, solar gravity slowed it. The non-gravitational effect did not cause the total speed to rise continuously after perihelion. It made the object slow slightly less than a gravity-only orbit predicted. This is what astronomers mean when they say it was accelerated away from the Sun. The phrase can sound as though the object switched on an engine and gained speed while departing. The actual effect was a small outward addition superimposed on a much larger inward gravitational pull. During much of the outbound path, the net acceleration still pointed toward the Sun even while the velocity pointed outward. Velocity and acceleration point in different directions for a receding object that is slowing. The Earth experiences the same distinction in orbit. Its velocity is roughly sideways, while its acceleration points toward the Sun. For Oumuamua, the small excess changed the long-term fitted trajectory enough to matter. Another common confusion concerns eccentricity. An eccentricity greater than 1 identifies a hyperbolic osculating orbit in the chosen gravitational model. Some solar system comets can temporarily appear slightly hyperbolic after close encounters with planets or because outgassing biases the fitted orbit. Oumuamua's incoming excess was much larger than those marginal cases, and its original orbit before significant planetary perturbation remained unbound. This is why the interstellar classification was secure even before the acceleration mechanism was understood. The non-gravitational force changed the reconstructed incoming direction and speed slightly. It did not turn a bound solar system asteroid into a convincing interstellar visitor. nor did the Sun fling it out from an originally closed orbit. A planet can scatter an object onto an escape path, but Oumuamua did not pass close enough to a giant planet during the observed encounter for that explanation. Its inbound motion already carried interstellar excess speed. The object fell into the solar gravitational well from outside, gained speed, rounded the Sun, and climbed back out. In an ideal two-body encounter, its speed infinitely far away afterward would equal its speed infinitely far away before, with only the direction changed. Outgassing or radiation pressure added a small amount of energy. The geometry resembles a stone rolling into a smooth valley and up the other side, except the path is curved in 3 dimensions and the stone never contacts a surface. The closest approach distance also needs scale. 38 million kilometers sounds vast, and it is more than 100 times the Earth-Moon distance. In the solar system, it lies inside Mercury's average orbit and close enough for strong heating. It was not close to the solar surface. The Sun's radius is under 1 million kilometers. Oumuamua passed dozens of solar radii from the photosphere. It was exposed to intense radiation without grazing the atmosphere or experiencing the most extreme tidal forces. The object's closest distance from Earth was also many millions of kilometers. A small change in path would not have created an immediate planetary impact in the way some illustrations imply. The encounter was scientifically close and physically remote. The direction from Lyra describes where the velocity vector pointed on the sky before solar deflection. It does not mean that the object traveled in a straight line from a currently visible location in Lyra. Constellations are projections. Their stars lie at different distances and move independently. Over millions of years, the pattern changes. Tracing the orbit backward is therefore not like extending a ruler to one star. It is a moving 3-dimensional problem inside the gravitational field of the galaxy. The term another star system is also probable rather than directly witnessed. Planetary ejection is the natural source of a body this size and composition. It may have formed around a star, a binary, or perhaps in a free-floating environment connected with star formation. No parent system was identified. Calling it a visitor from another star system summarizes the overwhelmingly likely formation context. It does not mean astronomers know which system. These clarifications remove false drama without reducing the true one. The object did not race toward Earth. It did not visibly fire a propulsion system. It did not point back to Vega. It did not have its shape photographed. It was a small, unresolved body whose orbit and brightness contained enough information to open a new field. That quieter description is also the more remarkable achievement. From angular positions measured against stars, astronomers separated solar gravity from a force 1,000 times weaker. From changing brightness, they inferred tumbling and extreme geometry without resolving the surface. From a trajectory lasting months, they established an origin beyond the solar system. The encounter demonstrates how little light can contain a great deal of physics when time is measured precisely. The entire chain of evidence becomes clearer when attention returns to the point of light in the Pan-STARRS images. The telescope did not know that it was looking at another planetary system. It measured brightness in a field. Software identified motion. A human compared nights. Other telescopes confirmed the path. The interstellar conclusion emerged from a chain of ordinary procedures applied carefully enough to reveal an extraordinary origin. There was no single moment when the object changed from asteroid to messenger. The evidence accumulated. At first, the orbit was uncertain. Then it became hyperbolic. At first, the body was treated as inactive. Then the trajectory revealed a weak force. At first, the brightness range suggested a long spindle. Then tumbling and alternative models allowed a broad disk. At first, only 2 interstellar objects were known. Then a third arrived under far better observation. The story itself has changed as the sample has grown. This is why the story of Oumuamua cannot be frozen in the science of 2018. The Vera Rubin Observatory is now surveying the southern sky, not merely waiting in a construction schedule. 3I Atlas is now part of the comparison, not a future possibility. Radiolytically produced hydrogen in water ice is now central to the natural discussion, while a pure hydrogen iceberg is only one older and more difficult proposal. Dark comets are now known as a broader population of apparently inactive bodies with non-gravitational motion. Scientific uncertainty remains. Its shape has become more precise. That chain also shows how different the same encounter could be during the Rubin era. Months before perihelion, an alert identifies a faint object with a suspiciously hyperbolic preliminary orbit. Within hours, other surveys recover earlier images. Within days, spectra establish color and search for distant activity. Space telescopes measure carbon dioxide, carbon monoxide, and water. The orbit improves. Astronomers trace the acceleration while the object is still cold. As it approaches the sun, cameras monitor rotation continuously. Gas production rises or remains absent. Infrared observations measure thermal emission and constraint size. Polarization reveals surface texture. Radar may be attempted if geometry and distance permit. If a waiting interceptor can reach the path, instruments pass through the coma or image the nucleus. This imagined campaign contains no guarantee of a simple answer. It contains enough independent measurements to prevent one missing observation from controlling the entire story. That is the legacy of arriving late in 2017. The visitor taught observers how to be early. There is also a quieter legacy. Before Oumuamua, the phrase material from another planetary system referred mainly to photons, cosmic rays, and microscopic dust. Afterward, another star system could be represented by a body large enough to rotate, erode, and carry an interior. The distance between stars did not shrink. The conceptual boundary did. Planetary systems no longer appeared as isolated disks whose debris remained forever local. They shed. The galaxy carries the fragments. Our system is embedded in that traffic. The traffic is thin enough that most nights reveal nothing. It is dense enough that 3 confirmed interstellar objects were found within less than a decade once surveys became capable. The next may already be moving inward, too faint for recognition. Another may be crossing the outer solar system now. Rubin's repeated images will turn some of these hidden paths into alerts. Each object will arrive with a different balance of time and geometry. Some will be found early. Some will emerge from the direction of the sun too late. Some will be active and bright. Some will remain point-like and quiet. The first visitor will gradually become one row in a catalog. Its mystery may diminish as analogs accumulate. A future object may behave almost exactly like Oumuamua while releasing detectable hydrogen. That would make the 2023 model look prescient. A group of flat volatile shards may reveal that collisional fragments dominate a size range. A population of porous inactive objects may show that radiation pressure is common, or no close analog may appear, leaving one eye as a rare outcome within a diverse population. The explanation that eventually survives may not be one spectacular revelation. It may be a combination, a water-rich, porous fragment, radiation-processed, eroded near perihelion, releasing difficult-to-detect hydrogen while tumbling in an unusual shape. No single word captures such an object. Comet may be approximately right. Asteroid may describe its appearance. Planetesimal relic may be safest. The formal designation avoids the argument. It is one-eye. Its role in history is independent of its exact substance. The first confirmed interstellar object crossed the inner solar system and was noticed. That fact does not depend on whether the recoil molecule was hydrogen or nitrogen. The encounter also established a practical ethical rule for future discoveries. Announce uncertainty quickly. Coordinate observations broadly. Preserve raw data. Search for natural and technological signatures without allowing either to dominate before evidence arrives. The response to 3I Atlas showed the value of this preparation. It also showed the danger of speculation spreading faster than measurements. Claims of artificial origin appeared early, while observations already showed a normal active comet with gas and dust. International scientific organizations responded by sharing accurate orbital and physical information. The lesson from Oumuamua was not to avoid extraordinary questions. It was to keep the scale of a claim matched to the scale of evidence. A visitor from another star is already extraordinary. It does not need to be a spacecraft to matter. A few grams of dust from another planetary system would be scientifically priceless. A 100-meter fragment passing within the orbit of Mercury is an event of profound value, even if every atom formed naturally. The natural universe is not the dull alternative. It contains planets torn apart, ices altered by cosmic rays, bodies thrown between stars, and molecules stored in darkness for ages before sunlight releases them. An artificial sail would change humanity's understanding of life in the universe. A natural interstellar comet changes humanity's understanding of how planetary systems exchange matter. Both are important. Only one requires evidence not yet found. The present balance of evidence is therefore not that the alien idea is impossible. It is that the object did not provide enough evidence to make that idea necessary. That balance also does not require pretending the natural mechanism is known. It is enough to say that nature remains the best supported category, while the details remain open. This balance can feel less satisfying than a reveal. It is more faithful to the visitor. Oumuamua did not preserve a complete answer. It arrived with constraints. Even then, the original question may never receive a unique answer. There is no law requiring every historical event to be reconstructible from surviving evidence. The value of science lies partly in knowing when the evidence stops. At the boundary, language should change. Was becomes probably was. Measured becomes inferred. Ruled out becomes constrained. Unknown remains unknown. These changes are not weakness. They are precision. The same precision protects wonder from exaggeration. Oumuamua does not become less remarkable when described as a likely natural body. Consider what natural means in this case. Matter assembled around a star we cannot identify. It may have formed beyond the snow line of a planetary disk before Earth existed or long afterward. Planets or stars rearranged its orbit violently enough to remove it from its home. It crossed a space so empty that a journey of millions of years left no witness. Cosmic radiation may have altered molecules inside its ice. A chance alignment brought it within a quarter of an astronomical unit of the sun's solar heat, awakened a process hidden through interstellar darkness. The resulting force moved a body whose mass may have ranged from millions to billions of kilograms, or less if it was extraordinarily porous, by an amount detectable from Earth. The body passed without collision. A telescope found it only after the crucial moment. Astronomers reconstructed the encounter from reflected light. Nothing in that sequence is ordinary on a human scale. No artificial purpose is needed to make it profound. The possibility of technology belongs in a different part of the mind. It is a reminder that unknown civilizations cannot be excluded from the universe by assumption. It is a reason to search for signals when a suitable target appears. It is not the identity that the present evidence assigns. The best current picture is more modest and more physical. Oumuamua was probably a small natural relic of planet formation, altered by ejection and interstellar travel, then weakly accelerated by a sunlight-driven process that escaped direct detection. The process may have been outgassing. The escaping species may have included molecular hydrogen released from irradiated water-rich ice. Its body may have been flattened, elongated, irregular, or marked by large albedo differences. Its source star is lost in the motions of the galaxy. This is not a complete portrait. It is the region of explanation where the evidence points most strongly. Outside that region, possibilities widen. Inside it, one fact remains simple. A fragment from another stellar system entered ours. The Sun did not capture it. Earth did not touch it. Humanity did not see its surface. Yet the visitor altered human knowledge before continuing outward. By now, sunlight at its distance is weak. The Sun would appear as a brilliant star rather than the overwhelming disk seen from Earth, still brighter than the surrounding stars, but occupying little of the sky. The giant planets lie behind. Neptune's orbit has been crossed. The object moves through the outer domain toward the heliopause and the interstellar medium beyond. Its speed relative to the Sun approaches the excess speed it carried inward, modified slightly by the measured non-gravitational effect. The tumble continues in darkness. One broad face, if it has a broad face, turns toward the Sun, then an edge, then another uncertain surface. No telescope records the sequence. The famous brightness curve has ended. The orbit remains in databases. The raw images remain in archives. The papers remain open to reanalysis. The object itself becomes physically inaccessible while becoming intellectually permanent. This reversal is common in astronomy. Light arrives and then stops. The event leaves numbers. Understanding continues after observation. Future researchers may return to the 2017 data with models not yet invented. Better knowledge of amorphous ice, dark comets, porous aggregates, and interstellar populations may change the probabilities again. A close analog may make one old hypothesis suddenly obvious, or the case may remain unresolved indefinitely. There is peace in that possibility. Not every messenger delivers a sentence. Some reveal only that a road exists. Oumuamua revealed the road between planetary systems. Borisov traveled the same road, carrying an obvious cometary atmosphere. 3I Atlas followed with a rich chemical display and a prepared network of observers. Others will come. The word first will remain attached to Oumuamua even after the object is no longer the strangest or best studied. First does not mean best understood. It means the boundary was crossed there. On October 19, 2017, the crossing occurred not in space, where the object had already been traveling for ages, but in human recognition. Before that date, interstellar planetesimals were expected. After it, one had a measured orbit, a name, and an unsolved physical history. The difference between expectation and detection can be only a few pixels wide. The night sky above Hawaii held no visible announcement. The telescope continued its survey. Stars remained fixed in the individual frames. One point shifted. From that shift came a new category of object, a debate about cometary physics, searches for technology, plans for waiting spacecraft, and an observatory strategy for the next arrival. The object did not stay. The change did. Far beyond the orbit of Neptune, Oumuamua is moving away from the Sun. Here, the first visitor remains in the form astronomy can preserve: positions, photons, limits, models, and questions. And above Earth, the surveys continue. Good night.